Good morning, everybody. Happy Wednesday. Everybody is doing well. Oops. I think my plan for today is kind of more review and question time. I'm not sure we have any formal lecture thing to go over. And we can always go back. So we'll also do some naming practice today and then do Lewis dot structures and stuff like that. And again, ask questions. So I'm going to start off with actually a question from lab. Since this came up this year and then it typically comes up in the past, let's see, let's do this one with magnesium. And let me just copy over the problem. And so it's this problem here where it talks about figuring out the average atomic mass. And so recall what we had said back in our previous lectures, right? So we said that the mass on the periodic table was the average, right, of all our different isotopes. And so now we're kind of working through, finding the mass on the periodic table essentially. And so the key parts here are also carrying our significant figures. So while our mass is reported to 5 significant figures, our abundance, at least in this case, is only reported to 4. And so that's also the trick in, the other problems in the lab and the post lab is just how many sig figs. And so it's good to do this step by step. And so let's go ahead and do that. So we'll start with our mass here. Oops. Apologize. So 23.985. So that's atomic mass units. And then we're going to multiply it by our abundance. So we just move the decimal over 2 times. Now that's multiplied by 0.7899. So you want to do the multiplication and keep the sig fig. So we'll do that and I'll kind of set up everything. But you want to go step by step. So you don't want to punch everything in on the calculator because you might lose track of your sig figs. So I'm just setting up our work. Oh, sorry, scrolling too wildly. All right, so now we have our work set up. And let me pull out my calculator. All right, so we'll do our first multiplication. So 23.985 times 0.7899. And so now that gives us, oops. All right, let me pull back up our calculator and see if I can do this. There we go. That's a little better so we can actually see that. Let's get rid of this. Okay. And so we do our multiplication. So we need to keep 4 sig figs. So we round appropriately. So that's 18.95. Okay, let's keep going. So 24.986 times 0.1. And I'm not going to bother putting in all the zeros in the calculator. But we know it's 4 sig figs. So 2.49. That would be 9 with rounding. And then our last one. And again, 4 sig figs. So 2.86, and then that rounds to 1. All right, so now we have this setup. And so now we have to do the addition, but now our addition rules for significant figures come into play. And so this means, let me change pens, that we can only report the 2 after the decimal place. So that's our limiting factor there. And so now let's just do that addition. So 18.95. And so I'm going to, you plug in all the numbers. So then we round to 2 after. And well, it just so happens that it only gives us an answer 2 after. So that works out well. So that's 24.31 atomic mass units. So does that make sense to everybody with keeping track with the significant figures and everything like that? Excellent. Just glancing through, if there was anything else that stood out. Again, ask questions if you need help. All right, let's go back to some naming. And let's start with number 4, because I didn't actually cover this one explicitly. So we have, see if you can figure out this first part at least, this beryllium sulfite. Oops, oh my gosh. Sorry, that's what happens when you're a chemist. So see if you can name it. Hopefully you didn't hear me give the answer away. And then I'll explain the water part. All right, so I gave it away a little. But yes, right, this is beryllium. Where's my mouse here? So our group 2, and then go back to your polyatomic sheet if you need, right? Have that handy. Oh, and there it is, right? SO3, and it's a 2 minus charge. And so that does balance in a 1-to-1 ratio. So that's good. Let's go back. So now we can write beryllium, sulfite. Now, what do we do about this water thing? So I didn't explain this, we didn't cover it, but there are some compounds that are complex with water. And so let's look up some. Let's see if the Wikipedia page is useful. And so magnesium sulfate, you may be familiar with this. So it's the form, you probably know it as, are Epsom salts. And so notice that this is a heptahydrate compound. So magnesium sulfate complex. And so now we'll see that we use a prefix to indicate how many waters that it's complex with. So that would be 7. So hepta is 7. So complex with 7 waters. And so you can see kind of the difference. So this is anhydrous magnesium sulfate for comparison. So it looks more like a dry powder. And then in this heptahydrate form, it has this crystalline structure. And let's see, I'm trying to find a picture if it shows how it packs. Since that's the significance, is it depends just how it binds. So notice it tells you at least the crystal packing. So this is indicative of the form it's in. I was just hoping for better pictures. There we go. This is what I'm kind of looking for. And so what I'm trying to show you is you have your magnesium chloride, and then your water is within the crystal structure. So it's actually part of the crystal structure. So let's go back in. So fascinatingly, magnesium sulfate can be complex with water in a bunch of different forms. So it has like a tetrahydrate, for example, this dihydrate. And again, it refers to the crystal packing. I was hoping for a picture. Let's see. Let's check this one. Not a. Oh, here we go. And where is our water? Trying to figure out this picture. Looking for our sulfate and our water. Sorry, they use different colors, so it's kind of strange sometimes. They didn't put a key. I think these are the sulfates. And I'm not quite sure where the waters are, to be honest. It just should be one water. All right. Anyways, so the point is that we need our prefixes to indicate how many waters. And so this is just a list of common prefixes. So this would be for hydrates. The only one that is not on this list is hemi. So you can have a hemihydrate where you actually have half an equivalent. And so I'll add that. So hemi would be half an equivalent of water. All right, so let's try to name some of these. So let's do the first three. Then we'll check in. So this one is interesting. So now we have to figure out the oxidation state of molybdenum. And so we have sulfate, which is -2. And so you could do your reverse swap trick and realize that this is a 3 and this is a 1, but sulfate is really -2. Or you could just do some algebra, which might be simpler here. So if a sulfate is -2, we have 3 of them. So -2 times 3 is 6. That means we have molybdenum 6. Again, for the oxidation state, sulfate. So let's try the next one. So this would be titanium. And again, we have to figure out the oxidation state. So this is nitrate -1. -1 times 3, -3. So we have titanium 3 nitrate. This is a good one too. So this is kind of an interesting one. So we have a H here bound to a metal. We don't often see this, but sometimes hydrogen can act as a hydride with metals. So sodium, aluminum, especially. And so this is called sodium hydride. So now try 5, 6, and 7. We'll go over them. So post your answers in the chat. And so let's look at this one. So this would be one where the reverse swap trick would work well. And so what I mean by that is we can take our 3 here. So it goes back, so -3, and that leaves 2 plus for iron. And yes, that is what phosphate is. So it's -3. Double check your sanity. So -3 times 2 is -6. 2 times 3, +6. So those cancel out. And again, now we have iron 2 for oxidation state, right? We don't put 3, we put the oxidation state. So iron 2, phosphate. So what do we think of 6? So 6 could be one of those that was confusing. And so you have to first kind of study it, figure out, well, how am I going to break this down? And so you want to recognize, well, this is actually a polyatomic. So that's why your sheet is kind of handy as you're kind of looking around. And get familiar with ammonia, right? That will come up a lot. So we have ammonium here. And then what was this one? So this was another one that I said watch out for. And so that's acetate. So we actually have ammonium acetate here. So it looks tricky, but not too bad. And so what's the last one? So what's that V stand for? And so let's look at, so H2PO4. So our V is vanadium. I'll at least write vanadium. But we have to determine its oxidation state. It's a transition metal. Again, go ahead and find it. Oh, there it is. Okay. So vanadium, and then H2PO4. So that's dihydrogen phosphate, and it has a -1 charge on it. There's 4 of them, so -1 times 4, -4. So that must mean we're at vanadium 4 and then dihydrogen phosphate. All right, let's do 8, 9, 10. Finish that up. All right, let's continue. So let's see if this one we can back out. So it gives us 7 plus 3 minus. That does match for phosphate. Again, sanity check, -3 times 7, -21. 7 times 3 is 21. And so that gives us manganese 7, so with our Roman numerals, again indicating our oxidation state, and then phosphate. So 9, so this is cyanide here, -1 charge. So that gives us iron 3 cyanide. And then this last one, so this is right at group 2. That's going to be barium sulfate. So let's try at least a few of these going the other way. So writing out our formulas now. So let's definitely look at, well, let's just look at the first 3 for sure. All right, let's look at these. And so now we have vanadium. So what was arsenide? So these tend to trip people up. But remember, right? Oh, we just changed the ending to "ide." So that's really arsenic. And we can look at our periodic table. Ah, there it is. So arsenic. So that means it's going to have a -3 oxidation state. And we can write that there. And so sometimes I do some scratch work on this side. Well, we have vanadium, and that's our oxidation state, 5 plus. Arsenic is 3 minus. And then easiest way is to swap them. And so that is our answer, V3AS5. All right. So now our next one, and again, we could write out some scratch work. So cobalt and then nitrite. So that's NO2, -1. And then our cobalt we said was 3 plus. And so again, we could do the swap trick. And that gives us cobalt, then NO2, all in parentheses, and then a 3 indicating that you have 3 nitrites. Our next one is yttrium perchlorate. So yttrium was one of those ones that we said was always 3 plus. So we can write our Y here. Maybe we can write our scratch work. So now look at perchlorate. Where's our perchlorate? So ClO4 -1. And now again, just swap trick. So that gives us, we need 3 equivalents of chlorate or perchlorate to balance out our yttrium. Does that make sense to people? Let's at least do these last 3, and then I think they'll be pretty good for practice for that. And so let's look at these. So we have silver. So remember we said silver was always 1 plus. And then again, we have this "ide" again. So phosphide. So that's going to be phosphorus 3 minus. And so that gives us silver 3, P, Ag3P there for that one. And so now let's look at this one, tin 4 selenide. So selenide is under this group. So those are all -2 oxidation states. So we have 4 plus, -2. So we can see I need 2 selenides to balance out this tin. And, oh, yeah, I made a mistake. So tin is SN and then Se2 there. Questions? And so now our last one is calcium sulfite. And so remember, sulfite is SO3 2 minus. Oh, cadmium. Sorry, cadmium. So calcium at first. Cadmium. So let's find cadmium on the periodic table. There's cadmium. So that's probably the 2 plus oxidation state. Yep, 2 plus there. So that helps us. And so that's already balanced in a 1-to-1 ratio. So now it's just cadmium. So CdSO3. All right. Any questions about that? And so just as a recap, right, we want to think about our oxidation states and our Lewis dot structures. And so I'm just going to rewrite them again. So kind of what we're doing here, but let's do it again. So now this is kind of our overview cheat sheet almost. And so we had said, right, we had our group 1, NS1. That means our Lewis dot structures. So sodium, lithium, right? All of those look like that. And they're all NS1. So now NS2, that would be beryllium, magnesium. So they all have 2 dots on one side. Again, showing how our electrons are filled in. So then moving over to group 3, so that's boron and aluminum. So that'd be NS2, NP1. And so we want to reflect that. So 2 dots on one side and then 1 dot on the other. It doesn't matter. Do gallium 2, something like that. And then group 4, so NS2, NP2. And so this is actually tricky. So most of them we'd want to write like this. So silicon and germanium, which is reflective of their nature. But carbon is special. So carbon, goes back to why we're carbon-based life forms. But carbon tends to hybridize. And so we reflect that by drawing out its Lewis dot structure like that. So carbon is special. And so let's finish out our trend. So then our group 5, NS2, NP3. So that could be phosphorus, nitrogen, arsenic. And so now we go down and we can also draw out the electron configuration like this, right? All different ways to represent the same thing. So now I'm showing how the next row fills in. So now we're at NP4, but I wanted to draw those lines showing how our p orbitals now double up. So one of them doubles up. So now we have two dots on two sides and then one dot left. And so now let's finish up with our halogens. So NS2, NP5. And so all our halogens have 7 valence electrons. And then finally our noble gases, group 8, NS2, NP6. So neon with all 8, same with argon. All right, that looks pretty good there. Any questions on that? Let's see, I'm just thinking of what we covered, things to practice. And then, let's just write with this, right, our oxidation states. And so let's write that. What color? Maybe this funky marble green. So, right, this is 1 plus oxidation state, 2 plus. This will help you see 3 plus. Remember, group 4 is that switch 4 plus 4 minus. And then now phosphorus usually goes -3 with ionic compounds. Then oxygen and all that group 6 is -2. Halogens -1. And of course, 0 for our noble gases. All right, I think that should put you guys in a pretty good place, at least knowledge-wise. So we want to put together these patterns, right? So you want your electron configurations to feel repetitive and kind of see what our electron configuration is showing us. And we're focusing on those valence electrons. And those valence electrons are related, right, to our oxidation state. So our oxidation state just kind of tells us how it's going to behave in an ionic compound. So putting those pieces together. And then it's on you to do a lot of naming practice. So feeling really comfortable with this. And then I'm more than happy to, again, meet individually with people and help people practice this, kind of go over tricks and tips and sort everything out. I'm probably going to end the live stream soon, though, since I think we've covered all the basics. Again, it's a lot of practice at this point, individual practice. And I'm more than happy to meet with people because it sometimes helps to talk through the naming and make sure that you understand it. And that's really part of learning, is being able to have a dialogue. So that's why I like to do it live. But not too many people, I think, are around right now. I know some people said that they really like this time, so I didn't want to move it. No one else expressed a better time, but I am definitely, again, open to suggestions of when I can have more live streaming office hours, because I think that's the best way to get the interaction. Even if you guys are in the chat, it is awesome. And of course, we can do Zoom, but there are other issues with Zoom, such as not being able to easily record and share with the rest of the class. All right, I appreciate it. Keep up the good work in the class. I have plenty of grading to do. You guys are keeping me busy, which is good. I appreciate that. And I will connect with y'all over email. I'll hang around on stream in case there are any questions. So be sure to pop in. Otherwise, I look forward to seeing you by email. Have a great day.